Good afternoon, Professor. Could you help me solve a problem?
Sure, Billy.
Thanks. Okay, Jimmy and I like to play on a seesaw. Jimmy is 210 pounds and I only weigh 140 pounds. If I sit 6 feet from the middle of the seesaw, how far does Jimmy have to sit if we want to be balanced? And by helping me solve this problem, I mean assist me in gaining a conceptual understanding.
No problem. Let's start at the very beginning. A seesaw can be modeled by a lever. A lever is a weightless beam that leans on a balancing point called the fulcrum. The distance from the fulcrum and the weight is the lever arm. Let's try putting a weight on the lever to the right of the fulcrum and take note of what happens.
The weight causes the lever to rotate clockwise.
That's correct. Aren't you a little Einstein, Billy? What happens if we move the same weight further out?
The weight has a greater clockwise effect.
Correct again. Let's keep the distance the same but replace the weight with a heavier one.
The greater weight at the same distance has a greater effect on the lever arm.
Now, what would happen if the weight were placed to the left of the fulcrum?
It has a counterclockwise effect on the lever.
Correct. Moving forward, now what do you notice when two equal weights are placed at equal but opposite distances?
It's balanced.
Yes, it is, and we say that the lever is at equilibrium. Okay, now let's try to place both of the weights directly in the center of the lever stacked on top of each other. What do you think will happen? Will the lever remain balanced?
I think so. Because the weight will be balancing on the fulcrum and not on any of the lever arms, so the lever arms will remain balanced.
Try it out.
I was right. Yay.
Yes, you were. For the exact reason that you said. If you place both weights at the midpoint, the lever arms will remain undisturbed. Also, if we put a single weight exactly at the midpoint, we will still have this equilibrium.
But wait, why does the distance and weight affect equilibrium of the lever?
Well, the weights and distances must be proportional. Meaning that if on one side of the lever the weight or the distance changes, then the other side of the lever must change either the weight or distance to keep the lever balanced. Or rather to keep the relationship between the two lever arms constant. Understand?
So, for instance, if I have two weights, one that is twice as much as the other, then can I try moving the lighter weight twice as far away and it will stay balanced?
Yes. Think you've gotten the concept.
Yes.
So let's go back to the problem at hand.
Okay. So my problem is that Jimmy and I cannot balance ourselves on a seesaw. Jimmy is 210 pounds and I only weigh 140 pounds. If I sit 6 feet from the middle of the seesaw, how far does Jimmy have to sit if we want to be balanced?
Okay, let's draw a picture. Pictures help.
Well, Jimmy, although rather large for a second grader, is 2/3 heavier than I am. So, that would mean that if I sit 6 feet away from the middle, then he would have to sit 2/3 closer to the middle than I would.
Exactly. Now, what would your answer be?
Well, 2/3 of 6 is 4. So he is to sit 4 feet away.
Correct. We can also represent this relationship by an equation. The weight times the distance one lever arm must equal the weight times the distance on the other. So our equation is W1 times D1 equals W2 times D2.
Oh, well, why didn't you tell me that in the first place? I could have just used a procedural equation this whole time. Oh no, now I understand how ratios work conceptually. Thanks, Professor.
So did we answer your question?
Well, yes, Oh, now that made me think of another question. What if my other friend, Bobby, wanted to be on the seesaw too? Could we both sit on one side of the seesaw and Jimmy on the other side and still be balanced? This is assuming that I still sit at 6 feet from the middle and Bobby weighing 80 pounds sits 4 feet from the middle.
For this problem we can continue to use our same concept of ratios, but now we can use our generic equation to model this more complex problem. Now we have many weights on one side of the lever and only one weight on the other side, but the two lever arms still need to be proportional to each other so we achieve equilibrium. So if we modify the equation given, we will now add the different components on that lever arm and then set them equal to the opposite side. So our new equation is W1D1 plus W2D2 plus W3D3 plus WNDN equals WD, N being the amount of weights on the lever with multiple weights on it.
Well, looks complicated.
At first, yes. So let's demonstrate this new equation on a simpler problem so it doesn't seem as complicated. And let's draw a picture to map out our balance. Pictures help.
Okay.
So we have 3 weights on one lever arm at 1, 2, and 3 feet away from the middle, all equaling 1 pound. And then there is only one weight on the opposite side 2 feet away equaling 3 pounds. Will this lever be balanced even though there is multiple weights on one lever arm, but only one on the other?
Okay, so according to our new and improved equation that would mean 3 times 1 plus 2 times 1 plus 1 times 1 which equals 6. And then looking at the other side of the equation we have 3 times 2 which also equals 6.
Correct?
Oh, well that didn't seem too complicated after all.
Yes, very nice, Billy. So back to our problem. Let's draw a picture. Yes, because pictures help. In our case, you weigh 140 pounds and are sitting on the seesaw 6 feet away, and then Skinny Bobby weighs 80 pounds and is sitting 4 feet away from the middle on the same side of the seesaw. How far does Jimmy, weighing 210 pounds, have to sit from the middle of the seesaw?
Okay, so our equation is my weight times my distance plus Bobby's weight times Bobby's distance which equals Jimmy's weight times his distance.
Correct.
Okay, so then we have 140 times 6 plus 80 times 4 equals 210 times Jimmy's distance, D. And 840 plus 320 equals 210D. 1160 equals 210D. So Jimmy's distance would be approximately 5.5 feet away from the middle of the seesaw for it should be balanced.
Correct.
Yay. I get it. So this would all mean that if I just so happen to gain some pounds, or if instead of Bobby sitting at 4 feet on the seesaw he would sit on my shoulders, then Jimmy would have to adjust his position on the seesaw outward to make his distance greater, assuming he would still be weighing 210 pounds, for all 3 of us to remain balanced.
Exactly. Awesome, Billy. I think you've got the concept of proportional reasoning.
Yes. Thanks, Professor. I have to go tell Jimmy and Bobby. Bye.
Bye, Billy.